Okay, we're live. Hello everyone. Welcome to a new stream. Hope the audio is good today. Right. So welcome everyone. We're picking up where we left last time, and we were last doing the SDL game engine in Golang, and where we stopped was we're doing the input system, where we're handling SDL's input. So we are reading all the states, and I think there was a disconnect. That's good. So we're reading, we're using SDL's poll event. So we're polling the operating system continuously for inputs, and we started writing routines to essentially have an input system that we can use later on to detect mouse and keyboard key presses, key releases, if you hold down a key, if you lift a key. And so we still haven't implemented that yet fully. And we also wanted to kind of start writing the rest of the game loop. So that's going to be the plan for today. We're going to try to finish the entire input system to the functionality that we would want. And then we can start looking into OpenGL, and that will probably be a majority of our time is spent on writing OpenGL and making sure that we know how to do graphics on the GPU. So let's get right into it. So from last time, poll events going to give us events that have been clicked or that have happened this frame, and we need to handle those. We need to read them from Windows before we can run any of our game logic. So if we look at our game loop right here, we're going to see that we only have handle inputs. Now, if we just fill out the game loop, just so we can kind of get an idea of what this should look like. Normally, we're going to handle inputs, that's the first thing. Potentially, we're going to run on game logic. So we're going to take this input, now that we have it for this frame, and we're going to run all the objects. So we're going to run the AI, move our characters, shoot any weapons that we have, and so on. And then we are going to, let's see, we are going to draw. So that will be the graphics step. So we don't draw until all the logic has finished. So if I move my player, then I'm going to first logically move them. So I'm going to change the positions, the coordinates, but they're not going to actually update on the screen until we have gone forward, right? Like until the draw step is when people will see that the character has moved. So that's our draw step. And then they must go in this order. So we have handle inputs, and then run game logic, and then draw. That's the minimum that's needed in this case. All right. So this will be for a bit later in a minute, but we can now continue with the first step every frame, which is to handle the inputs. So let's just try to run this, make sure everything is running from last time. I'm going to go run. There we go, and we have some button that we're displaying here. Okay, it's a right screen. So this, we're filling up a rectangle here, and then we have handle inputs, and every frame we are running our input key clicked. We're seeing if a key clicked. In this case, it's the A key. Right. Of course, this function is not correct yet, so let's go into that. So we have made a few functions. We have just written kind of the functions that we would like the input system to have, but we haven't implemented them yet. This is what we're trying to do today. So if we just look quickly to review them, we wanted a key clicked event to know when it was just clicked this frame, a key released, and then a key down, which is when I hold down a key. It doesn't matter if it was clicked this frame or not, as long as it's down, I'm going to continue to return true from this function. A key up, similarly, is whenever the key is released. It doesn't matter if it was this frame or not. And then the same functions, but for the mouse buttons. Right? So we have here, I think SDL supports up to 5, from what I have seen. So yeah, so let's look into that. Now, SDL does give us these events, these keyboard events, and if we look at it, we have the type, which can be key up or down. We have a timestamp, and we have, which we don't care about, honestly, the window, I don't think we care about. State, it's mostly the same, like from what I understand, as the type. So we're going to just choose one. The repeat is important because it's going to tell us, is this key being held down, right? Because if it changed state, it's going to reset to 1. Otherwise, it's going to be it's going to start increasing. Repeat 1, 2, 3, 4, 5, so on. And then the symbol for us is important because we're going to try to use this to know which key is being pressed. So since we are taking a subset of this data, we created our own struct, our own object. If I know where I'm familiar with Go, like a class, and we're just holding which key, the state, so is it pressed or not pressed, and then some information to know, okay, did we press it this frame or not? Now, we are going to have to remember, to provide all this functionality, we're going to have to remember the previous frame's state. So every frame we're going to get some events, and we're going to store these events in this hash map, right? But it's we're going to have to, every frame, even if we got no events, we're going to have to actually update this map. Let's see how we're going to do that and why. So in handle events, we are going to simply be reading keyboard events. So whenever the event loop, the event loop on the main thread is receiving events from the operating system, we're going to just populate this map. So we have this map, and what are we interested in? We're going to input the key, right? Depending, so if I have my A key, we're going to put that. If it's the first time that we see this key was pressed, then we're just going to fill up the key. State is already sent to us, so we're just going to use it. So it could be pressed or not pressed. And then whether this was pressed this frame or not. Now, if we're handling a new event, that means something changed with the key. Potentially it's a repeat, or it was just like it actually happened this frame, right? So we're going to check both for the state, and we're going to check for the repeat. But while this should be okay, there is a problem. So let's just run the window. Now, if I press the A key, now it's false because it's not being clicked, and I want to just detect the first frame when it's clicked. If I just click it, even though I'm just clicking really quickly and then lifting my hand, we can see that for multiple frames, it's true. Right? And this is because I'm so fast, or the computer actually is so fast that between the time that I click the button and I lift my finger, it's going to register many frames. And so this is not good for us. What we want is this variable here, these two must be reset every time. So what we're going to do actually is just before a new input event, or before we process the event loop, we're going to be firing another function here. So just before we handle keyboard inputs, let's say func event loop start. That's it. We're just going to kind of notify the input system that, hey, we're going to start a new event loop. Be ready. Do whatever you need to do. So right before the event loop, we're going to just say input, and let's, okay, right, this needs to be exposed publicly. And we're just going to start, nothing special. Now, here, what are we going to do? We need to reset any key that is press this frame true or is release this frame true, because since we hit this function, it's already been a full game loop. We have gone through the game logic. We have gone through the draw step and so on, and now we are back on the top. And this frame is not going to be enough for us to realize, okay, I lifted my hand from the key. But as far as the game goes, that's enough. We're not going to register 3 shots of your weapon just from one click. It's going to be one click. So we're going to reset this. So to do that, that's actually very simple. We're going to just iterate over the key map. And now every time, so this is a pointer, and so we can just edit it directly. So we are going to say is press this frame is equal to false, and is release this frame is false. We're going to reset them, because if they were true last time, then they are no longer true this time. The key doesn't change, and the state doesn't necessarily change it. State will change when we get the next event, so potentially in handed keyboard event. So let's now try again and see if we still get this issue of, if you zoom into this, we get the issue of getting multiple true events from one click. Like this. So again, I'm going to click A multiple times, and let's see, scroll up. So only one. Perfect. There we go. So no matter how fast or slow I kind of click the button, I'm getting only one true event. Actually, if I hold the button down, so I'm going to hold the A key, it doesn't matter. We are only getting one true event, which is perfect. So this system is now working perfectly, because the function we're implementing is key click. So we want to know only a click. It doesn't matter if I hold it down, I'm going to register one click. Amazing. So now with this done, it should be easy to start doing key release. Key release is the same thing, but we are just going to copy this, and we're just going to be using, instead of press this frame, we're going to be using release this frame. That should be enough. Let's try it out. So I'm going to switch this for the same key release for the A. Let's run. So now it should be false. I'm going to click. I'm holding it down now. Nothing. That's correct. Then now I'm going to lift my finger, and there we go. We have one true event when I first lift my finger, then nothing happened. So that's also correct. That's how to release. And this is actually, if you have done any Unity work or something like that, then this is kind of what's actually going inside. Or when you're running any application, really, it's always talking to the operating system, getting events, and then any of these more advanced behavior on top of simple, got clicked, got released is done on software like this. Okay, let's do key down. So in key down, it's not actually about, key down and key up both. It's not about the key being this frame. It's about the state of the key. So as long as my key is in a specific state, I'm going to return true. And we're going to say the state is, and if we look at the keyboard events, then SDL dot, where is it, dot state, right, is either pressed or released. SDL dot pressed or released. So we're going to say is the state equal to SDL? So this is down, so this is pressed. Is it pressed or not? This is going to be true. Doesn't matter if it's this frame or that frame, as long as it's down, it's going to be true. And then key up, similar, but you're just going to say released. There we go. Right. Now, there is one thing we have to do additionally in key up, which is what if we have never seen the key before? If this is null, that means this key has never been pressed. But for key up, which must return true if the key is not down, then it doesn't matter if we have never seen it before. If we have never seen it before, that just means it's up, it's released. So in this case, we can also return true. That's, I think, the only situation where in key up we also return true. Right. All right. Now, for mouse clicks, let's see. Let's just take this. Oh, actually, take it from here. There we go. Just kind of prepare it. Now, for mouse clicks, let's see. We had a different loop because mouse events are different. So if we look at what's in a mouse event, we have a mouse up and down. So that's similar to the state. Actually, there we go. We have a state, press release. Window, we don't care. Okay, we have a button and only a few buttons. So left, middle, right button, and then 2 additional buttons. So if you have more buttons on your mouse, that could be any one of them. It's going to register X1, X2 to these. And then clicks. Okay, we're going to need to handle clicks as well. So let's see, and the coordinates. Since we are handling events now, we don't care, but in the future, definitely. When we start taking mouse movements to the left and to the right. Okay, so now we could combine this, but I think just to keep things simple, maybe we can separate this since this is taking a key code. We can potentially break it up just to keep it simple. Just check the chat. Okay. So. I think just break it up just to keep things simple for now. So we're going to create a similar struct to this, and let's do mouse state. Right. Now we're going to have a key, say it's an int, so that's mouse, left mouse button, right mouse button, so on. State, and then similarly is pressed. This frame is released, this frame, and so cool. For a mouse, we are also going to want to know if it's a double click. So we'd say is double click or double clicked. Yeah. There you go. And the key, so in a mouse event, the button is a uint8. Yeah, int works. So button, yeah, that's the button actually. button, and then the mouse event also gives a state. That's press release, okay, and clicks. I don't think we care about the actual number of clicks for now, but definitely if it's double click or not. So we're just going to do that one through this variable. All right. So we have this now. Similarly, now I'm going to also create a map. Here we're going to say mouse button map, and then it's going to be indexed by. We don't have a key code coming from the mouse. The mouse only sends us this button. Int 8. So let's just say it's an int. There we go, and it's a mouse state. It's not the mouse state, it's a mouse button state. There. Okay, that's good. Now, handle the event. So it's going to be very similar to this. Let's just start with this. We're going to take the events and we're going to check based on the button. All right. So actually just pass it to int, and this is the mouse button map. Just say mouse button MB. Okay, so if we don't have it, we're going to just again create it. Mouse button state. Our button is e.button. There we go. And then we're going to add it to our map. Right, so mouse map index by e.button equals. Yeah. So if we have never seen this key before, then we're going to add it to the map just to keep the record. And then now in this case, since we have so little, you can actually hard code. You can just have a bunch of variables for the mouse, but nah, I think it's okay. It's very simple, I guess. So the states is very straightforward. It's again just a state, so it's the same thing. Is press this frame. We're going to use the state again, but then we don't have a repeat on mouse button. What we have instead is clicks. Yeah, I mean we could use clicks, not really, or we could use is press this frame itself. So you say if it's press this frame, it must be not press this frame. If it's pressed now, no, then it's going to alternate. Let's see. Who has ideas in the chat? Yeah, I guess let's see how it reacts. So let's remove this. Not going to work. Going to have repeat. I would like to see how SDL treats this. Press equals released, and then this is going to be actually this could be now. Yeah. If it's pressed this frame, it's only whether we got an event saying it's pressed, and since it's a mouse, we are not going to get any repeat, so we are only going to get this event once. So I think for a mouse, we only ever get one event when it's pressed, one event when it's released, and that's it. We don't get any other events. So that should be it, actually. Yeah. Okay, we'll try this out. We're just going to, of course, the same way we were doing for the key map of resetting it every frame just before the start of the loop. We're going to do the same for the mouse button state. And this time, is press this frame is false, is release this frame is false, and then is double click this false. Let's see. So we double clicked, we haven't handled yet. Let's look into that. So is double clicked. So let's do clicks. So the information for clicks is 2 for double click, etc. So it actually can register more than 2 clicks. So if you keep clicking, I assume it just keeps going up. For us, we don't care about that, so we're going to just say if it's exactly 2, I think. So if you click once, and then on the second click, not on the release, on the second click, we're going to register that as click. Yeah, let's see. So clicks is 2, and it's pressed. Sorry, and e dot state is pressed. Yeah, I think that works. This should work. Now, of course, we're going to have to test all of this. We have some error down there, right? So the mouse clicked is going to be basically the same thing, but I'm going to use this mouse button, and then it's not there, and we're going to say it's not clicked, and it's wrong. And use only by, oh, okay. Okay, it's not there, then it's false anyway. Otherwise, it's this. So let's test that. Now, we're running this, and we are firing the mouse event. Okay. Now let's take this part, prints to the screen. Let's put it in the game logic, and let's just print if input.mouse clicked. So which mouse button? So let's say left. I think it's button left. Yeah, button left. Okay, see that mouse. Going to get all false. Click a release again. So this looks actually amazing. And that's it's right. Then again, I have another click here. So if I click, yeah, just registers exactly 1 click every time. That's good. Mouse released, it's supposed to be, so if we just log like click and release together for the same button, we're going to get 2 true values, one next to each other per click that I do. Let me see, 1 true. Yeah, only 1. Let's look at release. So release is, oh, okay, we have now. So let's do release then. Let's do that. And for release is release this frame. We're actually going to want another function which says whether we have double clicked the mouse. Double click. Yeah, which mouse button and whether you have, yeah, so you can double click essentially any, you can even double click the right mouse button. We get that, but this time we're returning is double click, and the release is whether this is released. Mouse down is simple. We're just going to say it's very similar to the keyboard events. Whether the state is pressed, doesn't matter if it's this frame or not. Then mouse up. So mouse up again. We're going to say if it's not there at all, then for sure it's up. Like what will it be? So this and the state otherwise is release. Right. So let's test click a release, and then let's test those two. Then if I click, there we go. here is a true event, here is a true event. There is a delay of a few frames between them because it takes time for me to lift my finger, but we get one registration on when I press down and then when I lift my finger, but nothing else. So we're almost done with the input system. Now let's just test our double click and mouse up and down. Let's do up, mouse up, down. Just run up for now. Okay, so it's true because it's just up, even if I haven't clicked it before. Now if I hold down, there we go, it's all false. If I lift it up, it's again true. If I click just for a bit, let me get it correct. Okay, let's check out what's down. Now it should be the opposite behavior. It's all false, and then when I hold it down, all true. And when I lift up, it's all false again. Nice. Can actually commit this. And then, okay, yeah, double click is double. Mouse double click. And we're checking for the left button. Let's see if a double click actually works. So click, nothing, click, double click. Oh, wow, we got this. Nice. This is working. So we have an actual input system akin to what you might find in another game engine, implemented all from scratch. It's amazing, I think. This is all using a little bit of a few functions, not very long, very simple code, right? But we have basically learned how to use the events sent by the operating system and then build on top to get additional functionality like this press, release, this frame, and so on, which normally you wouldn't get. Like the OS wouldn't tell you, oh, this frame doesn't have this concept. The frame is within the concept of the game itself. So to be concrete, the frame starts at the beginning of this loop, this game loop. So starts with the inputs and then ends with the final step. In our case, it's just draw. You might have, potentially you'll have a physics step somewhere, but in general, at least for this one, it's going to stop here. So after draw, you have finished your frame. So yeah. Okay, that's good. If we had a character, something moving, we'd actually be able to move it. But let's leave that for when we do OpenGL. All right, so what's the time? Cool. Let's discuss OpenGL or rendering. So now we are done with inputs. That's all done. We're not going to, I think, go back to this for a while. Can move this, keep the logic empty. Let's go back to rendering and I guess discuss OpenGL a bit. And now, here right now, we're not using OpenGL. We're using some SDL functionality like fill right. We're giving it, we're saying, take the entire screen and then fill it all up with this one color. And then update the window. If we don't update, nothing happens, but yeah, so that's why we get red. If I change this, we're going to get a different color. Now what's happening behind the scenes is SDL is issuing some GPU commands, and the GPU is taking care of filling up the entire screen, right? Of drawing the actual pixels in the window. Now we don't want that. We don't want SDL to be doing this work. We want to take full control over every stage of the process. Now let's talk just a little bit about kind of, I think, OpenGL, what it is, and then we'll go into drawing that and install. Is it installed? I don't think we even have it installed. Interesting. Yeah. Okay, then, all right. Let's get that, and then we'll talk about it along the way. So I open up my browser now, and I'm just going to say, go OpenGL. Right. So we want to run OpenGL with Go, and we're going to need, let's see, It's the bindings, right? Okay, so Go bindings for OpenGL. So it has these installations. So OpenGL has all these versions, but once we have them, we can init and then draw. Now our window for us, our window is going to be created through SDL, but after that we can init GL and then draw it. And if we look at the examples, yeah, we'll get into all these nice vertex buffer pointers. Let's go check their example. You just kind of go through. 21 is a bit old, but here they're using the LFW. It's fine. Don't care. Yeah, they're just issuing GL commands. Okay, so let's just get this set up first. So these are all the versions. Now, on most modern machines, they are going to be able to run OpenGL 4.x. These are the latest, like 4.6 is the latest. And then OpenGL has two modes. One is the basically immediate mode, the very old way of doing things, and which is also very slow compared to now. But that's called compatibility mode. Or you can run OpenGL in core mode, which is completely disables the old way of doing things. And the only way it allows you to do it is through the new way, where you have vertex buffers and all these pointers and vertex array objects and all these things, which we'll get to. But first we need to install either all of them, if you like, or one of them. So let's actually, I'll just run this if I don't mind. Take these. Plug them in here. So I'm going to say, for now, give me compatibility. And I'm just going to run 4.6. So go get v4.6 compatibility GL. This. Take a minute, and then we're going to need, I think that's it. This is actually enough for us. Then we're going to be able to do this. So while this runs, let's look into this. We're going to, when we create the window in SDL, we're going to say window OpenGL. So we're going to create a window in such a way that we prepare it. It's creating what we call a context. It's creating a place for OpenGL to run, you could imagine. So we're going to create it that way, and then once that's created successfully, we're going to plug in the OpenGL command here. I think I already have it, but let's use 4.6 GL. Wow, that's taking a while. Okay, come on, go. Do it. You can do it. So that's what they mean here, only in the context of an active context, which we have. If we fail to initialize OpenGL, then something really bad happened. No, we won't be using fixed pipeline. This is only for demonstration. We're going to be using the new programmable pipeline. That's a good question. Well, I'm just going to use it for demonstration, because we're assuming that we don't know what OpenGL is. We're starting completely from scratch. Right? Yeah, man, that's still going on. That's impressive. Is this in? Okay. So for us. Now we're going to, let's see. We're going to be running context. So now let's start with OpenGL, honestly. Let's not wait for this. It's taking too long. Let's just start talking about it. OpenGL is, you can imagine, a library. It's a spec actually, for how your GPU, for how you can program your GPU. Just like we have SDL, we have an API to talk to Windows or Mac OS. There is a spec, a way of talking directly with the GPU. And if you want to do that nowadays, you know, there is Vulkan, there is DirectX on Windows, but OpenGL is cross-platform, which makes it very nice. You can actually find all the functions that are available on the GPU that you can use. Because these GPU manufacturers, like NVIDIA or AMD, they take this spec, okay, finally installed after 4 minutes. They take this OpenGL spec, they implement it. And the inputs or outputs are, you know, specified by the spec, but not the implementation. So NVIDIA is going to have a different actual implementation of OpenGL, let's say 4.6, than AMD, but it's going to be the same functions. And when you update your drivers, right, your GPU drivers, what you are essentially doing is getting the latest version of all of these implementations on your GPU. So when we first start talking to the GPU, we're going to set some functions. We're going to initGL, right? And we hope everything goes well there. Capability. We're going to start setting some settings. So let's say init OpenGL. So what do we need to do? We can, if Go can actually run. Come on, Go. Okay, just make sure I'm using the right version. Finally. Cool. So init, yep, now we're getting the whole thing. Set attributes. Yeah, I think it can be slow because it's just so actually realized, yeah. Okay. Set attribute, yeah. So we're going to be setting a few options. One thing is the version. Which version are we using? So we're going to say, okay, SDL. So we have the OpenGL version is like this. It's 4.x or like x.y, right? And this is called the major version, and then this is the minor. So if we're using here 4.6, then we're going to need to set the major to 4 and the minor to 6. So we say SDL.major version. There we go. And here it just takes an int, so we're going to say it's 4, and then same thing. If I want 4.6, this is going to be 6, but I'm going to say here minor version. And you can set all kinds of settings on OpenGL here on this OpenGL context, essentially through SDL in this case. And this we are only going to do in the beginning. So perhaps you want to say, what is the default color? The default color might be black, might be white. So we're going to say SDL dot again GL set attributes. Now let's see, alpha. Actually, let's set the colors. That's, yeah. Let's set the pixel sizes. So we're going to need to say here, for each pixel on the screen, how many bytes or how many bits is that pixel? If you're using HDR, I assume you guys have heard about HDR. It's getting more popular nowadays. If you use that, then what's essentially happening is each pixel is no longer 0 to 255, and this is the kind of the classic way is you have red for each pixel, you have red color, red, green, blue, and then red is actually a number from 0 till 255, and similarly for green, similarly for blue. Doesn't have to be this way, but this is usually what it is, right? So we can actually set that. We can decide how big our colors are. And for now, since we're just doing SDR, which is the normal range of colors, we're going to say red size. So it's the size of R, what's the size of G and B, and this is going to be in bits. So 255 is 1 byte, which is 8 bits. So say 8, and then we're going to say green size, and then we're going to set also red, green, and the blue size. We're going to also want to enable double buffering. So double buffering is when you're drawing to the screen, you don't actually want to immediately update the window. Otherwise, your logic has progressed only potentially so far that you have partially changed the screen, and then so the bottom half of the screen of the window is the old frame, and the top half is the new frame that you have, and then you have kind of this break in the middle. It's not clean. The update is not clean. So what we do is we actually use double the memory. We have a front buffer and a back buffer. The buffer is just an array. It's basically all your pixels. So let's say you have 1 million pixels in front of you on your screen. So we're going to prepare 2 million, not the 1 million we actually need. When we draw new stuff, we draw them to the back buffer. So we draw to the ones that are not shown on the screen, just so we don't affect what the user sees. The user can actually see a static image for a fraction of a second. When we're done fully drawing that back buffer, we're going to swap the buffer on the screen. So the one that was displayed is going to be taken back, and the one that we filled up is going to be shown to the screen. So in a way, the user sees the entire screen all at once, the entire rendered image. So we're going to say, hey, we do want that. Usually, like since forever, basically, double buffering has been enabled. So we're going to just say, set it to 1, like true, set it to true. And I think it's about right. You might want to set the actual buffer size to the window. Yeah, I think that's okay. Let's see. I think the last thing is, do we want to run compatibility, which is what's called a fixed function pipeline, or we want to run in the new one? So for that, we're going to set a new attribute, and this is GL. Let's see, profile. I think profile mask. Profile, and then GL context profile compatibility flag. It's flag file core context. So what we're going to actually do in the end, or not in the end, but just a bit after, is we don't want this. We want profile 4. So in the old way of doing things, when you wanted to draw something, so let's say you wanted to draw, I don't know, a box on the screen, you would send the position of each point needed to draw the box at the moment you wanted to draw it. So if I want to draw, if I need 4 points to draw my let's say my square, then I'm going to at that moment send 4 points. And then if I have 2 squares, I'm going to send again 2 squares from the CPU to the GPU. So all the time I'm going to be sending stuff over. And this process is very slow. It's not high performance at all. And so what we want to do is instead predefine, we want to, all this information about the stuff that we have, we send them once to the GPU and it's stored on the VRAM. So when you buy a graphics card, it's going to say there's 2 GB of VRAM or something like that. And that just means it has RAM locally on the GPU that the GPU can immediately access without the CPU interfering. So then the CPU can send all of this data once, and then later on, if it wants to draw that square, it doesn't need to actually send it all the data all over again about all the points and what the color, the position of the points are, and so on. We just say, you draw that specific box, and it already knows because it has it in memory, in the GPU memory itself. So the core way, and this is how the new way is done. This is called the programmable pipeline. This is what core means. Core means enable only that. Completely disable the first way. Even if I try to use it, just give me an error. Compatibility says both work. We're going to use compatibility just for a small demonstration, but aside from that, we're going to go full in. We're going to write parsers for the shaders. So we're going to read the shaders, we're going to compile them, have all of that nice stuff. So we can write actual GLSL code on the GPU. But let's start with this. Any questions so far? We get into this. I think all is good. Okay. So we have this. I'm just going to move this into a function just to be clean. So init GL to take all of this. Here. Okay. That's good. Now we don't want a surface, so we no longer want this. We don't want this. I think we can remove all of this. I don't think we need surface. We need just a context. So just here, I'm going to say window. So before we did, surface, give me the surface, and internally STL is handling all the magic. We don't want that. We want to do things manually. So we're going to say, we have, as you can see, some GL functions, GL something. So we are going to say GL create context, right? And say GL context and error. If we failed for some reason, error is null, then we're just going to say crash the app. Okay. Something is wrong here. Failed create OpenGL. And and this context doesn't really have functions. It's just it's there for us to essentially use. Although we need to defer delete. Delete. No, it's delete. STL. STL. Okay, delete context. This is just cleanup when we're done. So we create the window and we set, this is important, we set that it's an OpenGL window. And then we create the context that we can use then to draw in. Then we initialize all the stuff that we want, any settings. Of course, we can change them later on, but I think these are sensible defaults. Okay, I think that's good. We can now look into shaders. So a shader is a program, just like we are coding right now, that runs on the on the GPU instead of the CPU. And the language that OpenGL uses is called GLSL, like OpenGL shader language. So you write them, you write your shaders, which are the GPU programs that tell the GPU how to draw. You write them on the GPU, right? Sorry, you write them in these files, and then we load them into the GPU. So we have the it's called simple.vert shader. It's good. Frag shader. Okay. Now these programs, they look a lot like C. So you usually start with font version, and we just specify, hey, which version? Like, am I on? Like this. We can actually look into. Let's look into OpenGL. We don't that. Okay. And just add GLSL to be specific. Let's see, shaders. Yeah, this is by the way an amazing resource if you want to learn anything about OpenGL. It has a ton of stuff completely free, and we can just take a sample program. Let's see. Let's take a Vertex. Our Vertex shader is going to be very simple. Let's take this, and then we're just going to simplify it. We don't need all of that. For us, it's 4.6, right? Here it's saying core. We can say compatibility for us. Let's remove this. We'll talk about this later. We'll talk about this later as well. Just want to get the bare minimum. This. We don't. So Vertex, and then let's get the fragment shader. I'm going to explain those in a minute. We'll go to the fragment shader thing. So it's 4.6. You actually need a fragment color, and then let's just set that to some, let's say to red. RGB. Yeah, RGB. Let's put this right. Now, let me get a drawing board. Let's talk about this. Okay. So, and I think we touched upon this last time. Won't work. When you have so GPUs nowadays, they always deal with triangles, which is very interesting. But even if I want to draw a box on the screen, how does the GPU draw this? How does the computer understand I want to draw this box with this scale and so on? What we do is we have these things called, we have a vertex. At each, what we send is not actually this entire thing. The GPU doesn't see this. What we send to the GPU is only a bunch of points. That's literally it. We're going to say, here's a point. Here is a point here. We're going to send potentially 4 points. It's like this. That's it. Now, so each point has a position at least, but it can have more attributes, we call them. And we're going to go into all of this and see how all of this works. But at the very least, each vertex, each point we send has a position. So in X, Y, Z, for example. Now, what the GPU is going to do is going to draw triangles between each 3 points, depending on the order or the way we send it. So it's going to say that, okay, between this point and this point, and this one and this one, that's one triangle. And then between this, and this, and the first one again is another triangle. So a box on the screen is actually rendered as two triangles by the GPU. And this is why now games, they want more and more triangles, because the more triangles we have, the more geometry, the more things we can have on the screen, the more realistic the graphics look. If you saw, how blocky PlayStation 1 or old games like that, how blocky they look, it's because they had so little triangles. And when you have so little triangles, you cannot make surfaces smooth, because even a circle is actually drawn as a bunch of triangles usually. So, and you can see this if you have a 3D program like Blender, 3D modeling program, you will see this. You see how this works. So, for example, I want to draw now a circle. Sorry, that's a bad circle, but I want to draw a circle. How am I going to approximate a circle using triangles? So you can say, hey, maybe I'll put a point here, and then let's do it I'll put a point here, and then I'll put a point here, right? Maybe here like this, right? And then I will do potentially another point here, and then from this, because each 3 points, we need 3 points for triangle, and then maybe a point here, a point here. As of course, there are more ways of doing this, but that's definitely one way. So look at the actual shape we got versus the circle. It's extremely blocky. It's like it's basically a pentagon. It's not circle at all. Now, but imagine we start adding more and more points. So instead of the points being this far away, so having a little number of points, a small number of points, we're going to really put them very close to each other. So instead of this being the closest to each other, I'm going to put in the center, at the top, and then right next to it here. So what's my triangle now? Okay, that's starting to kind of line up there. Then I'm going to put one next to it here, next to it here, next to it here, and so on. And then each 3. I'm still drawing triangles, but now if I continue this process, you can see it's actually looking curved. It's actually matching what a circle would look like, at least from far away, much better. And this is why, as GPUs get stronger, they are essentially able to draw more triangles. Now we're reaching millions. Now we're in the millions per frame of triangles, right? The higher number of triangles we can draw, the more realistic we can make our graphics. Either more realistic, or we can do more things. Like we can add more things on screen. Right? So this process of taking the vertex, putting it somewhere on the screen, so on, this is handled by the Vertex shader. So the Vertex program that runs on the GPU, and the process is generally like this. So we have the Vertex shader, and that eventually ends up reaching the fragment shader, like the pixel shader. Fragment shader. Right. In here, the input. So the vertex shader, you can imagine, runs per vertex that we have. So if we have, to approximate just this simple circle, we might have, I don't know, 50 or something vertices, right, or more. So this is going to run 50 times. If we have 50 vertices, this is going to run 50 times. If we have 50 million, this is going to run, 50 million times. So for each single vertex on the screen, this is usually going to run at least once, and it's going to position its output. Its job is to say, okay, this vertex ends up on this position on the screen. Once that is processed, Once that's done running, the fragment shader runs not per so here the inputs, let's make it blue, the input is vertices. For the fragment shader, it's not exactly input, but you can imagine the input is actually pixels. More or less, for each pixel on the screen, the fragment shader runs once. Now that might say, okay, that's not a lot, but if you have a full HD screen, like 1080p, that's 1920 multiplied by 1080. That's already in the millions of pixels. So it's going to run a million times for a single frame. So let's say it's a million times. So if I'm running 60 frames a second, I'm potentially drawing 60 million pixels a second. I'm setting the color. I'm running a function 60 million times a second, and that is setting the colors of all the pixels on the screen. So we are able to fully write, just like we write normal C++ or C code or Go code. We are able to write these functions and more. Nowadays, you have tessellation and geometry shaders, tessellation shaders, and compute shaders if you just want to do some calculations on the GPU and make use of the high parallelism. Yeah. So our journey in OpenGL is going to essentially be first being able to write these shaders and then compile them and load them on the GPU. We're going to be able to, we will need to be able to send a list of vertices to the GPU. So we say, here is a list of vertices, and here is my vertex shader, here is my fragment shader. Now draw, right? And then it's going to run whatever code we give it. Now let's go back to the code. You can see right now we're doing something very simple. For the vertex shader, we're simply saying, hey, it's the position of the vertex, same thing. I don't want you to move anything. Just GL position is the output in this case, so we set this function. On the fragment shader, we need to set frag color or some other output that is a like a vector for 4 elements, X, Y, Z, and W. W is the alpha here, RGBA alpha. So we just set. Now, if we do this, then we are essentially running this function for each pixel, and then each pixel is getting the same output. So they're all going to be the same color. If we have a texture to look up from, or we have like some more advanced logic, then we're going to have all the colors on the screen. We're going to have characters drawn with specific colors on them, so on, depending on texture, depending on the position on the screen, so on. So let's start with that. Let's start preparing this. So I wrote these shaders into this kind of a resources folder. Now we'll need the code to actually load them. So let's have a new Go package called shaders. Called shaders.go. Let's see. So we're going to be able, we're going to need to parse. So to run shaders on the GPU, we need to take these files, essentially compile them, just like we compile any code. We need to put all the parts of a shader and then compile it all at once. Because, like I said, right, the shader is going to be made of multiple parts. Vertex shader then goes to the fragment shader, so on. All of these together, they make a shader program on the GPU, a single program, and I can have multiple programs on the GPU. So we're going to say a shader is essentially, we're going to, for a single shader program, we're going to load at least one vertex shader and one fragment shader, and this is what we'll do now. So let's say, well, let's just do load shaders. Let's do a function, and let's put let's have a struct, call it, let's just call shader, right? Shader program, so we don't get confused. Now each shader, and we'll see the GL code for this, but each shader on the GPU has an ID. So we're going to need for the shader program an ID. I think that's a uint32. You can fix this, it's wrong. And then let's say we only have vertex and fragment shaders for now, so we'll say vertex vert shader ID again, and then fragment shader ID. So we kind of have a program. We add all these different shaders from the files, and then we link them. We make them one complete program. Then we don't need these independent vertex and fragment shaders. So first thing we're going to need to do is we actually need to load these files. So we're going to say os.open file, yes, file, and you just open it simple. So what are we going to need to load? So resources slash shader slash simple dot vert shader. I think simple and shader. Yeah, we even get better. Better coloring, some. Oh yeah, this is undefined. Vertex shader. Need an in. So, like we said, you know, the vertex shader takes a list of points and operates on those, so it's run once per point. So we need, and this here, yeah, we need an input. We need a vert position as an input, and then we produce. So we get an input. So we're saying here is a point. Here is a single vertex coming in. Calculate the final position, because maybe I want to move it around, I want to do something with it, I want to scale it up and down. So we're going to take it, we're going to do something to it potentially, and then we're going to output the final position. In this case, it's one-to-one. We are not doing anything to it. We're just saying, I take it and I show it as this. And the fragment shader doesn't have an input in this case, but it just needs to output. This is the job of the fragment. So this should be a correct fragment shader, and this is a correct a vertex shader. Right. So let's go back to our shaders. Simple.js. And we're going to actually just read all the text. Read all. Read file. os.read file. Okay, let's use that. os.read file. So we give a name of file, and then we get the contents. Awesome. So this is what we need. So we say, okay, vert shader text, and then error. Something happened. Okay, if error is null for now, it's going to crash. Program. Error logger, break a line. Someone has questions, ask me, please. Feel free to ask if anything is confusing here. But yeah, let's do scale, calculate the vertex, shader. There we go. And then we're going to do the same for the fragment shader. Simple.fry. So you can see we even called it the same thing, simple.vert and simple.fry. So it's one shader, and then it has these two components to it. Awesome. So, shader. Now, let's use some OpenGL. we're going to need to do a few things. I'm going to say we're going to tell OpenGL create a new shader program. Just prepare it for us, and then we're going to create a new the two shaders essentially. So let's say kind of add the vertex shader to the program, to the shader program, and then 3, we're going to add the fragment shader, and then we're going to link the program to make it all kind of executable, all of it. Okay, sec. See. Anyone on the chat has questions? Okay. Okay. So let's start with the program. This is more or less the steps. I'm going to say GL reducer 1GL 46 compatibility. Okay. So we're going to say create program. The GL has a ton of functions. If you want to look at those, it's a huge list. That's why having resources next to you, like Learn OpenGL or the actual spec, can come in handy. So we're going to just create a program, right? It's going to return a UN32. So we were right. So most of what we do, or a lot of what we do on OpenGL, is going to be through essentially pointers, IDs for each thing we create. So it's going to give us back an ID. So if I say var my shader, and I just made the start because later on we can write the code in a nicer way. But then the shader is a shader program, right? This, and then the shader dot ID equals this. Okay. All right. So we're taking the ID, we're storing it. I'm going to leave checking errors for later. In this case, it's easy. If it fails, an ID must always be bigger than 0. If it's 0 or something else, it's something went wrong. So we can say if the ID is 0, then we can just crash. Now, hopefully you have better error handling later on, but that's not important. Okay. So if it failed, create shader program. Okay. Now let's do GL. Now we're going to how are we going to do step 2 and 3? And this is called attaching shaders. To add each of these individual shaders, we are going to need to attach to that to the program. So you can see it takes a program and it takes a shader. Right? So the shader we haven't created yet, we'll create, but essentially we'll need to put the shader.id, and we're going to need to put for example, the vertex ID, the vertex program ID. Then same thing, but again, one time with the fragment shader ID. And then you can imagine if you have more, you have compute shaders, you have other shaders, you have even maybe multiple fragment shaders. You just attach everything, and then at the end we link all of this, link program. And again, it's asking us for ID. So you can see OpenGL is kind of like a big state machine. We just tell it, hey, do this, and it's going to be more obvious why it's a state machine maybe next time. But yeah, we always need to refer to the thing. It doesn't remember what we are doing if we don't give it ID. So it's our job on the CPU end to kind of store all these IDs and then send them back when needed. So this should be it for this. And we're going to link Now we need to, what do you call it? We need to do the shaders. So just like the program has an ID, we also need this to have an ID. So let's check shader. I think not the shader source. We can actually compile. Create shader. Yeah. Create shader. There. So we have create program and create shader. Program is a collection of shaders. Right. We're going to need to compile our shader program. So let's do this. It's GL see. Yeah, we need to read it. And then yeah, so okay, I think we need to tell it the type of the shader here. So create shader takes the type, so can we say fragment shader variable. So we are going to need shader, but fragment shader ID. There you go. And then let's just put this vertex. So to create a shader, and then it's just asking essentially X type. The names can be confusing, but X type is the type of the shader that we're doing. Say okay, so we created those. This is vertex shader ID. So now we have IDs for both, and we are using these IDs later on to attach and link, but we haven't actually given the source code that we read here. And this is where we need to take this text, then send it to OpenGL to compile. So we are compiling it into programs we can actually use. So we have this, we have that. We're going to now let's take our source and send it. So we say GL shader source. We're going to essentially upload all this the string of data for each file, for each shader. We're going to upload it. It's going to say, where do you want to upload it? You can see it replaces the source code in a shader object. Our shader, so let's first deal with the vertex shader. So shader, the vertex shader, what does it want? It wants a count, it wants a string, and a so I think count is 1, because we are only uploading one program. The string, we can use a helper function, gl.string. String. Yeah. So it takes a list of Go strings and returns the C, because we need to deal kind of in C. And in C, when you have a string in C and C++, the last letter of the string must always be the null character. This is how classically we used to know, okay, I reached the end of the string. If I see this terminating character, then we know, okay, we reached the end of the string. So we're going to take our shader program, like the vertex shader, and then we're just going to add this terminator at the end. So let's do the vertex shader text. I'm going to add to it that we're going to add to it the terminating character. That's it. That's all we're going to do. Now this gives us back a C string, which is in the proper format that we want, and then a free function, and it just says, hey, when you are done using it, it's not going to free. So when you are done, you should free the memory. So we're going to say, okay, we're going to take the vertex C string and vert free from this, and we're going to defer the vert3. And then this one, we're going to just put the vertex C string, and then the length. Length, I don't think we need to specify. Yeah, that should be it. So we load the text, we create. We're creating our program, we're creating our two shaders, and then we're just, this is kind of annoying, but something we have to do because we're working in Golang. We're converting these strings into the proper format that OpenGL can understand just by appending into this, and then we're using strings to basically get pointers to these strings in memory that we have to later free by ourselves. So there's a little bit of manual memory management here. And then finally, we just upload all this text or the source code into the GPU. We're going to repeat the same thing for the fragment shader. Let's see. So let's put this here. This time it's the same idea, but fragment shader text, fragment C string, and frag3. Frag3. Then we're going to GL shader source. We're putting the source, but this time on the fragment shader ID. Again, we are uploading one shader and fragments. There we go. And the last thing is to just compile. So there shouldn't be anything else. So the last step is let's compile shader. You can say, okay, which shaders? So we have two shaders to compile in our case. So we have the we have the shader, we have vertex shader. If we're lucky, this should work. Right? So we have created a new shader program on OpenGL, and then we added two shaders, which we then uploaded the source to them. We compiled both of them, we attached them, and we linked. Right? So I think that should be. Let's run at least to check that we don't have any errors. So I'm going to do it in main. So just after we init OpenGL, let's do shaders dot shaders. Okay, and see if this doesn't go. Okay, that's good. We still have our inputs responsive, but it's all white. That's good. So this is kind of the default background, no crashes. That doesn't mean we compile successfully or that they are running. We simply uploaded them to VRAM, that they are there on the GPU. We're not using them yet. Probably we'll do that next week, but at the very least, we want to be able to kind of have gone through the flow. It's a bit long, but luckily it's something you only need to do once. Now, what we need is a way, and this is kind of very weird format, but we would like to get our shader errors and maybe make it specific, so like get compiled. So now at each stage, especially on, like here we can check if the ID is 0 and we'll know if something went wrong. But when we compiled, compilation might fail. Maybe I missed semicolon here, right, in GLSL. How do we know that something went wrong? Because unless we crash the GPU and our entire program with it, we're not going to know. So we can get logs essentially out of OpenGL, out of the GPU, and we can query what happened. So let's say right after compilation, after compiling the first one, we can say get shader compile errors. Now this is not the simplest thing, but let's just do it. So we can extract, just like we can set things, we can retrieve things out of the GPU. So we're going to say, hey, give me some specific values. And in this case, just so you get the format, here we're saying an integer vector. So vector of ints, this is what we are retrieving out of the shader. Now we're going to say, okay, get shader compile errors. So we'll say shader ID. Let's say UN32, essentially a pointer. Shader ID. What do we want? What's the parameter we would want to get? And then the output for the map. Returns a parameter from a shader object. So we can see in GL. So what's the name of the parameter? There is something called compile status. So we can retrieve, we can ask the GPU first, hey, for the last compilation that you did, what's the status on that? What happened? Is it successful? Is it not? And then we can say var is, or let's say compile successfully. And what does it return? That's an int32. Okay. Int 32. Now it wants a pointer, and it's going to fill it up for us with the result. So it's not returning the value, it's just filling up the parameter. And now we can say if not, let's say if compile successfully, then we have nothing to do with it. If it's 0, actually if it's true, GL true, I think it's 0. It's defined as 0. Actually it's defined as 1, yeah. It's then false is 0. So we're first asking, we say, hey, get me a parameter, get me an integer. That's why it's an IV. Get me an integer out of the GPU. Which thing do we want to get? That's the compile status, and then we are filling it up in this variable. Then we are checking. If it's true, then we have nothing to do. There were no errors. Everything's successful. Otherwise, we can say, we can print, error. Let's just see in general if we got actually any error. So we have one here, one here. On this one, we're going to give it the prime shader. On this one, we'll give it the vertex shader. No errors. There we go. Very nice. So let's actually try doing something wrong. So I'm going to remove the semicolon from this file and going to run. There we go. Perfect. So we are actually able to detect whether the compilation of the GPU program has failed or succeeded, not just Go. So Go might succeed, the shader fails. So now we are able to actually know this. Okay. Now we might want to know not just whether we succeeded or failed. We would like to know, hey, what's the exact error message? What happened? Which line maybe, so on. We can extract that out of the GPU by using what's called an information log that exists on the GPU. So it's a similar thing. We do GL dot, I think it's get info, not ALB. Get shader info log. Right. It's the same idea. We're giving to the shader, and we're saying, hey, any information you have on that shader, give it to me. We need though a buffer, and then we need somewhere, like it's just the same way that we gave it a variable to give us the status. We need to give it a variable so that it can fill in the string, the message that happened. But we don't know how big we need that. We need our buffer to be how big is the buffer for the message. If the message is very long, we're going to need a very big buffer. So we're going to say log length, right? And I think int32 should work. Yeah, work fine. And then GL dot get, I think it's also get shader IV. And then we have the shader ID. The name is GL info log length. There we go. So have that same thing. We're passing. So if we reach this point, we know for sure there is going to be an error, and so this log length is not going to be 0. Right? So we are first saying, okay, how big is the buffer that's needed? And then we're going to need the actual buffer, or log, let's call it log. And we need to do similar thing to what we did here. We cannot use our own strings, unfortunately. We're going to need to use this GL stuff. So let's do GL. So we want a string, and we just want kind of a big string, big enough and completely empty. And so we can just repeat. We can say, hey, potentially repeats, fill it up with nothing. Nothing is this null character, filled up with nothing. You know, how many times, how many characters does this string have? That's our log length. So we're going to essentially keep exactly enough room to fill up all the characters coming in from the GPU. So we have this string of the exact size that we need, just convert it to GL string. Just convert to GL string. Should be good. So now we have our log, we have our shader, and we can start passing it. It's asking us for the buffer size. Buffer size we know because we got the log length. So that's our size. And then length, I don't think we need, do we? We don't need. And then the actual buffer, which is log. And then this should fill up this buffer with the message on the GPU. And then we can just print that. And to print it, again, we need now to convert back. So gl.string converts from a Go string to an OpenGL or a C string. And now we need a function to convert from a C string back to Go. So we can use gl. Let's see, yeah, Go string. Yes, helper functions for us. So we give it a C string and we get back a Go string. So let's put the log pointer. There we go. So we have error message. Now we can just print that. Let's say shader compilation, or let's say compilation of shader with ID, and the ID is shader ID. The ID failed. Error is this error message. So again, for us, we just remove the semicolon here. Let's run this. Right? There we go. Very nice. So we have compilation of shader with ID 3. So that's our ID. Failed, and we say, okay, error 000, syntax error, expected this, got this, so on. Perfect. And I think this is the line number 8. Yeah, exactly. Line number 8 is even giving us the line. And if we fix this, we run again, no errors. Nice. There we go. So I think that should be good for today. Okay. Does anyone have any questions on the chat? But I think we made good progress. We finished our input system, and we are actually able to, we can clean up this code next time, but at the very least, we are able now to write GPU programs, send them to the GPU, fully compile them there, and then create like a ready shader that can be used to create graphics, which we'll see next time. So next time, we'll send some vertices to the GPU, and then tell the GPU, hey, use that shader that we have uploaded previously on these vertices. So it's going to use that vertex shader and that fragment shader. And the nice thing is, for the same set of vertices, we can on the fly, since all these shader programs are on the GPU, for the same set of vertices, we can just say, hey, change from using this shader to this other shader, and you would get like completely different effects. You might have, changing color, or you can have screen effects or anything you like, simply by saying, instead of, for example, drawing everything in red, I'll have another shader that's doing it in green or something. So that'd be very exciting. But yeah, so OpenGL can get a bit long. It's not as straightforward as writing, as we write with our tools on the CPU. But once you have everything set up, it becomes a lot easier to get things running. So we'll hopefully do that next time. Yeah, and we'll probably clean all of this. Why is this complaining? So we clean all of this, maybe refactor it into some functions that we can actually specify with shaders. We don't want them hard-coded, and just kind of have a better structure for everything. So far, this is good. And then if we actually manage to make it all the way next time, we can then look into having some stuff in the draw function. And once we have the ability to draw some basic things, like draw some different objects, we can actually start working on a game project just to test out very basic implementation. So something simple. Some simple game like, we're going to name this space shooter game, Space Invaders. Maybe Space Invaders, some very basic Space Invaders or ping pong or something. Just to play with the engine, play with the inputs, see how we can create graphics and do logic. And then we can continue working on the engine itself. So eventually we would like to do 3D graphics as well. So we can load, we should be able to load PNGs, so 2D images, 3D images, objects like out of Blender, and even sounds and whatnot. And down the line, physics as well. We'll need that, like proper physics engine. Probably use a library for that, or if people are interested, we can look into writing, at least partially writing our own collision logic. That's also very interesting. So yeah, thank you all for coming, and I'll see you next week, same time. That's will be our schedule. Thank you everyone, and have a good day.